Hello, welcome to this video. In this video, let us take a problem on Carnot cycle. Let us read the problem. A Carnot engine working between 400 degrees Celsius and 40 degrees Celsius. So, the moment we see that this is a problem on Carnot engine, we can straight away write the diagram in PV as well as TS plot. Alright. So, let us draw that first. So, we can write Carnot cycle in PV as well as TS diagram, and we know that the PV and TS diagram for Carnot cycle. So, we know that there will be heat addition in isothermal process, isothermal heat addition 1 to 2, reversible adiabatic expansion 2 to 3, then 3 to 4 that is isothermal heat rejection, and then 4 to 1 we will be having reversible adiabatic compression again. This is where we are supplying heat, this is where we are rejecting heat, okay, and this is our temperature constant, this is our reversible adiabatic, and this is also temperature constant, this is also reversible adiabatic compression. And then we have we can see that in a TS plot it is a constant temperature, all right. Then isentropic looks like a vertical line because entropy remains constant, or PV power gamma is equal to constant. Then again constant temperature heat rejection and reversible adiabatic or isentropic compression. So, here it will be 1, 2, 3 and then back to 4. Okay. This is our TH, that is temperature constant, higher temperature. This is our heat supply, this is our heat rejection. So, do not worry about these numbers. Different books may start one from here 1, 2, 3, 4. So, that is okay. All right. So, every notation, I mean, even if you start from here, the answer would be same. Okay. So, next, the temperature is 400 degrees Celsius and 40 degrees Celsius. Now, according to our notation, we have used temperature TL, lower temperature is 40 degrees Celsius and higher temperature is 400 degrees Celsius. And remember, temperature must be in Kelvin for efficiency, because we can check it if we want to. Now, for Carnot engine, we have this equation 1 minus TL by TH. Okay. Now, we can cross verify this. This cannot be simply 1 minus lower temperature is 40 by 400. Now, this answer is going to be wrong. We can cross verify. Temperature must be in Kelvin. Very important. Temperature must be in Kelvin. Okay. So, first thing is, first we will convert this temperature into Kelvin. Now, this is 40 plus 273 and 400 plus 273, all right. So, 40 plus 273 and 400 plus 273. 40 plus 273, 313 Kelvin, 313 Kelvin, and 400 plus 273 is 673 Kelvin. Okay. And the first sub question is thermal efficiency. So, we will find out the thermal efficiency first. Okay. Then second sub question is the heat added. So, heat supplied must be found out. And sub question C is entropy changes. So, we will find out change in entropy during heat rejection process. So, we are talking about process 3 to 4 then, because heat rejection is happening in process 3 to 4. All right. Now, let us start from the first sub question, that is A, efficiency. We already know, we have derived the equation for thermal efficiency for a Carnot engine is 1 minus TL by TH. Now, we will cross verify 1 minus TL is 313 divided by TH is 673. What I am trying to tell is that these two answers are not going to be same. Temperature must be in Kelvin. Okay. So, 1 minus 313 divided by 673. So, the answer is 53.49 percentage. Of course, we are multiplying it by 100 to keep it in percentage. So, 53.49 percentage. 53 point, so multiplied by 100, 53.49 percentage. Now, what I have told you is this 1 minus 40 by 400 is not going to be same. So, that is why temperature has to be in Kelvin. Okay. So, 90% is quite unimaginable for a heat engine. So, that also we must have an idea. So, temperature must be in Kelvin. So, these two answer is not going to be same. Temperature must be substituted in Kelvin. Okay. Now, let us go to sub question 2. Sub question B, we have what is the amount of heat supplied. So, sub question B, we must find out QS. Now, we know the efficiency 1 minus TL by TH is derived from efficiency can be equal to what? Efficiency is equal to work done by heat supplied. Okay. Efficiency we have. If we know the work transfer, we can find out QS. I think we missed that data. It was given here. Produces 130 kilojoule of work. So, work done is given. I mean, work transfer is given. So, work transfer is 130 kilojoules. So, since work done is known to us now, we can find out the heat supplied. Now, efficiency is our we have found out in the first step 0.5349, that is 53.49. Since I am not using 100 here every time, so I am while substituting I am just substituting it as 0.5349, because if you substitute 53.49 and divide this, if this goes to this side, 53.49 divided by 100, it will be 0.5349. So, I am just avoiding writing that every time, alright. So, 0.3, if you are not comfortable this way, you can straight away use that 53.49 and 100 here, that is also fine. Okay. So, now we know that work transfer is 130 kilojoules. Now, heat supply can be found out. And what is the unit of heat supply which we are going to get here? Since this has no unit, whatever work transfer we supply, if we substitute it in kilojoules, it QS will be in kilojoule. If you substitute work transfer in joule, this will be in joules, because this does not have unit. Whatever unit we substitute W in, the same unit will be of QS. So, therefore, QS will be equal to 130 divided by 0.5349. Okay. 130 divided by 0.5349, 243.036 kilojoules. Now, this last sub question, that is sub question C, what is the change in entropy during process 3 to 4? And remember, change in entropy is given by Q by T, alright. Now, that is Q 3 to 4 or Q rejection if we know, and if we divide that by temperature of 3 to 4 is TL, we must be able to get change in entropy during process 3 to 4 or during heat rejection. Now, how do we find out this Q 3 to 4? Now, we have since we have W, we can use the same logic, that W is equal to heat supplied minus heat rejected. Okay, already I am using negative, so everything what we get will be positive. It not necessarily tells you that is rejected or supplied. But what I am trying to tell you is change in entropy will be negative in fact, because heat is rejected during the process 3 to 4. All right. So, but however, this answer will be positive here because I have already used negative sign. So, work is 130 kilojoules and heat which we have found out is 243.06 minus QR, or we can say the QR goes here 243.06 minus 130. So, everything is in kilojoule, that we have made sure. 243.06 minus 130. Okay. So, 113.06 kilojoules. So, that is our QR actually. So, as I said, we are saying that QR is heat rejected, we will get it in positive because the moment I say heat rejected, I have used this negative sign. But in fact, if I write heat transfer, it has to be negative because heat is rejected. So, this I can write, this is minus 113.06 kilojoule because heat is rejected, or heat transfer, we know the sign convention, if heat is rejected is negative. All right. So, now we will come back here and substitute that this is minus 113.06 divided by temperature in Kelvin, lower temperature is 313, and remember the unit kilojoule per Q is in kilojoule and temperature is in Kelvin. So, it will be minus 113.06 divided by 330. That is minus 0.3612 kilojoule per Kelvin. So, this is how we solve Carnot cycle problems. Make sure that temperature is in Kelvin. Thank you.